right? The basis contain this many matrices. So here's a canonical basic. Say, let me call Eij. This set form a basic. Say 1 less than equal to I less than equal to M. So M rows and column. Then we have M by N matrix. Set of matrices. The set of matrices. So let me write like this. Eij is an M by N matrix. M by N, and Eij is the ijth entry is 1 and 0 otherwise, and the rest equal to 0. So for example, okay, is this clear? For example, if we talk about, say, 2 by 2 matrices, this space of 2 by 2 matrices, E11 would be the matrix, like position 1 is 1, the rest is 0. E21, for example, this is 0, 1, 0, 0. Right? We already talk about the ijth entry. 1 entry is 1, the rest is 0. 1 2 entry is 1, the rest is 0. Similar, we can do it for M by N matrices. All the entry are 0 except the ijth entry. And how many vector here? How we have M by N vector or M by N matrix here, right? Because it's like a matrix of M by N matrix, M row and column. And the first matrix E11, second one E12, and we have M by N matrix like that. And they form a basis of the vector space Rmn. So now we need to prove that. We show that Eij is a basis of Rmn. So to prove this is a basis, we need to prove two things, right? The first thing is they are linearly independent. And the second thing is they span the whole vector space. Right. So for linearly independent, here we always start by considering the equation C1, say C11, E11, right? C12, E1 matrix E12, C1n matrix E1n, C21 to C2n E1n, CM1 EM1 plus CMN EMN. Right. This one is a linear combination of these many matrices, right, in Rmn. And we have M by N matrices like that. This is equal to 0. So vector 0 in the vector space Rmn is a 0 matrices. Is a 0 matrices. So M by N, right? M N. So it's 0 matrix. All the entry is 0. The type of this matrix is M by N. Okay, so this is a system with n by n variables, right? The left hand side here for C11, C1n, C21, C2n, CM1, CMN are just real number. This one is equivalent to the matrix C11, C1n, CM1, MN equal to the zero matrix. Right, because this one is just the position 1 1 is 1 and the rest is 0, so it's C11, 0 0 0 0 everywhere else, and then plus 0 C12 and 0 everywhere else, and you just take the sum. We have C11, C12, C13, and then C1n, and so on. So this is equivalent to C11, C1n, CM1, CMN are on 0. This means that the set of vector or set of matrices Eij's is linear independent. And now this span R Mn, let's say matrix, say A11, A1n, AM1, AMN. This matrix is an arbitrary matrix in Rm by n, and this matrix can be written as, say, matrix A can be written as a linear combination of all matrix Eij, right? We have A equal to A11 times each 1 1, A1n E1, AM1, AMN EM, N. Right. In other words, A can be written as a linear combination of Eij, and this is arbitrary A. So this proves that span, this says span R n by n. So both two conditions, linear independent and span the whole vector space, they are a basic. This set is a basic of Rm by n. And these sets contain exactly n by n matrices. Therefore, the dimension of Rm by n is n by n dimensional. If we want to do that, we try to find a basis, and then the number of the vector in the basis is a dimension of the vector space.